Good morning, I'm Jay. I'm here to talk about our next generation gasoline engine, skyactiv-x. To understand how we're using skyactiv-x as a means to achieve our goals of sustainable Zoom 2030 to reduce our CO2 footprint by another 30%, we have to go back to this ideal engine roadmap that Dave pointed out. Now, the roadmap we've always known shows a convergence of gasoline and diesel engine technologies as the path towards the ideal internal combustion engine. Now, Dave's already worked and showed how we achieved major breakthroughs with the skyactiv-g engine, our current skyactiv engine, through a greatly increased compression ratio. Unlike skyactiv-g, skyactiv-x makes its gains in a totally different way. Skyactiv-g does it through a lot of mechanical means, pistons, injectors, compression ratio, headers, of course. In skyactiv-x, which we dubbed skyactiv-x because it's kind of the intersection between diesel and gasoline combustion technologies, we're making big gains through a process called lean compression ignition. We're essentially burning the fuel in a totally different way. So it's not as much through mechanical means. We're just burning the gasoline in a different way. Okay, so to understand lean compression ignition, we need to do a little bit of combustion science and review. So we'll start with lean. Obviously, if we want to reduce our CO2 footprint, we're going to have to reduce the amount of fuel that we're going to burn, right? And that's lean. Inside of an internal combustion engine, there's a chemical reaction that happens. It's called oxidation, where you have fuel, oxygen. They're split up and rematched with a new partner to create carbon dioxide and water in the ideal case. Now, if you have a situation where you have more fuel than you have air, this ideal ratio, then basically it's a rich condition. There's more fuel, everything breaks up, but the fuel molecule doesn't have an oxygen molecule to get mated up to. They don't have a dance partner. So in essence, the fuel molecule gets blown out the exhaust, or it gets wasted as wasted energy or as emissions, right? So a simple way to look at this is it's like having too many guys at the dance, right? There's a lot of wasted stuff going on. In the ideal case, there's a partner for every gas molecule, every oxygen molecule, and that's what we call stoichiometric. Basically, everybody gets paired up, everybody's got a right dance partner, and this is the ideal combustion case. Now, in a lean mixture, which is what we're trying to achieve, there's more oxygen than there is fuel. The oxygen doesn't find the fuel molecule to pair up with, but it's not wasted energy. It hangs out inside the cylinder, and this oxygen can actually absorb some of the heat of combustion and help with the expansion. This, in my analogy, is having more ladies at the dance, which I don't usually complain about. Okay, so lean combustion is good, but it also has a lot of benefits. In addition to reducing fuel, which is our overall goal, lean combustion actually has a lower flame temperature. It's physically cooler, okay? So when it's cooler, it also means that we waste less heat that's absorbed by the engine, and it forms less emissions, namely nitrous oxides. So as you can see from this graph, which shows an air-fuel ratio expressed as lambda, or you kind of think of it as a lady ratio. Greater than 1 is lean, more oxygen available. Less than 1 is rich. So on this scale right here, which is just a normal range of engine operation, lean to rich, we see a very big spike in emissions at stoichiometric, and also the highest temperatures at stoichiometric. In skyactiv-x, we're talking about a much leaner ratio. We're talking beyond 1.6 lambda, sometimes up to 2.5 lambda. You can see that these trends continue to drop. It still gets cooler. We still have less emissions as we get leaner and leaner. So lean burn is actually a really good thing. The problem is that burning lean gets difficult. The less and less fuel that you have in a mixture, the harder and harder it gets to ignite. Just like lighting your barbecue without enough lighter fluid, it has a hard time lighting off. Here we see a picture of, from the top of the cylinder, but basically this is the combustion flame lit by a spark, and over the same amount of time, or crank degrees, it's expanding relatively quickly across the cylinder or combustion chamber. Now, if we had a lambda of 2, basically twice the amount of air that we ideally need, we run into a problem. The flame, over the same amount of time, gets really slow. We can't get the energy out of the fuel in a fast enough time to make useful work out of it. As you get leaner and leaner, it gets so hard that eventually you can't actually light a spark. You can't actually make the thing combust. Again, back to your barbecue and charcoals. So that's a problem with lean burn, and that's why we don't use lean burn in most production cars. It just it gets to a point where there's so little energy out of the lean burn that you're using, you end up stepping on the gas more to compensate, and you end up using more fuel than you would have in the first place if you were just that stoichiometric. Well, it turns out that if you have this very lean condition that's very difficult to light. If you just took that and you kept on compressing it, and you made it hotter and made the pressures higher, it eventually gets to a point that everything spontaneously ignites all together at the same time. That's called compression ignition. It's similar to the compression ignition inside of a diesel engine, which we all know is very torqueful, very efficient, but it doesn't do it through fuel being injected. In a gasoline engine, compression ignition is typically often referred to as homogeneous charge compression ignition, or HCCI. I think some of you guys might have heard of that term before. HCCI basically is homogeneous because all the air and fuel inside the cylinders is already pre-mixed. So all you have to do is squish it down and boom, it lights everywhere. And you can see this right here. Over the same amount of time, at lambda 2.5 times the ideal amount of oxygen necessary for normal stoichiometric burn, you get this very, very rapid expansion of the flame front. Basically, all the energy in the fuel is being extracted over a very, very short period. So that's a really good thing, very efficient. Because it happens faster over a shorter period of time, we can actually get a lot more work out of it. Now, we all think of, as Dave described in the ideal internal combustion, we all think of, okay, the spark lights and the fuel, everything lights and goes boom at the same time. But in reality, it takes time. There's a flame front that has to spread across the piston. In a normal spark ignition engine, because it takes so long to burn across the cylinder and extract all the energy from the fuel, we typically have to light the charge before the piston reaches top dead center. That means the piston is still moving up, but we're already building pressure. The piston has to fight against the current, if you will, of the pressure. We have to do this so that we can get peak pressure over a range of time so that we can get the most work out of this downward stroke, the most pressure over the downward stroke. Now, if we did compression ignition, it happens over such a short period of time, we can actually target the peak of the pressure right after top dead center of the piston. So all that energy is released immediately, and bam, the piston just pushes down with the greatest amount of force. I'll point out that these two humps or domes actually have the same area representing energy. So for the same amount of fuel, we can get a much higher pressure out of our combustion process through compression ignition than we can through traditional spark ignition. So that's the benefit of compression ignition. Okay, so now that we kind of understand what lean compression ignition is and the benefits of it, we can talk about it on our roadmap and explain how it affects these 7 thermodynamic factors and how we make these improvements from skyactiv-G to skyactiv-x. Green means the most ideal case, of course, and then orange or red means areas that needs improvement. Lean compression ignition, mostly the greatest impact it has is on specific heat ratio. As Dave explained, it's a difficult concept, but basically now with lean compression ignition, we are using less gas, but we're expanding the gas in the air and the fuel mix inside the cylinder the same amount. We're actually getting more with less. So that's this huge change in specific heat ratio. In skyactiv-G, it was compression ratio that made the big change. specific heat ratio is the big next leap for skyactiv-x. Also, because it's faster, combustion speed increases, and also, and now that it's faster, we can place it at a very ideal spot. Again, right after top dead center, we could get the most out of the bang. Some indirect effects is, well, in order to have compression ignition, we mentioned that we have to squeeze this balloon, we have to squeeze this we have to increase the pressure so much that we require a much higher compression ratio, more so than in the skyactiv-G, which was, you know, world leading at the time. And now that we're expanding the gases, now that we're have a much leaner mixture, we're putting a lot more energy into the gas instead of into the cylinder heads or into the combustion chamber. Sorry about that. So anyway, basically there's less heat loss. Okay, we're putting the energy of the combustion into the gas to expand the air and the gas inside the cylinder instead of putting it into the walls and having your radiators and your cooling system having to deal with it. And of course, because it's a lean combustion, we're putting a lot more air into it so that we reduce pumping losses. The throttle plate is open for longer. We don't have to suck through a very small straw all the time. Okay, so everything we talked about so far, HCCI, compression ignition, these are all accepted theory. Most engine nerds all understand this, and it's been a target for all of us to go after. But it's been very challenging. There's a reason why we don't have HCCI in the broad market right now. One of the biggest challenges of HCCI or compression ignition is controlling when it happens. Now what I mean by this is that if you think about your standard gasoline engine, the gasoline engine starts the combustion process by using the spark plug, right? The spark plug lights, it initiates the flame that expands, and the flame expands out throughout the combustion chamber. By using the spark plug and what we call spark ignition, we can control exactly when the engine combusts. Similarly, in a diesel engine, which uses compression ignition, all the air inside the cylinder is compressed at a very high pressure and temperature. And we control when that lights off by when we inject the fuel into the cylinder, right? It's so hot that the instant that the fuel gets squirted into the cylinder, it lights immediately, and we have, again, combustion timing. The problem with HCCI is we don't have that control. Whenever the fuel and the air inside the cylinder reaches a critical temperature and pressure, it's just going to go boom, right? So that's really the challenge of HCCI. And because of that, it results in a very limited range of operation for conventional HCCI. Only in this very limited range of engine loads and engine speeds can we have ideal combustion timing, the peak of the pressure rise right after top dead center. Outside of that, we might have a very delayed combustion, or we might have very advanced combustion, which could result in very bad things. So this is a big problem. A lot of other OEMs have struggled with this. And this also means that even if you want to run an engine with HCCI, you're still going to need a spark plug, because anywhere outside of this range, you need to have a spark plug to operate in normal gas combustion or normal spark ignition modes. And when you do that, basically anytime you accelerate, even a light acceleration, you might have to transition from a spark ignition mode to a compression ignition mode back to a spark ignition mode. That creates a little bit of a problem, because a traditional HCCI engine, every time it switches modes, there's a momentary pause. And that pause causes a stumble in drivability. So every time you step on the gas, you might get one stumble, then another stumble as it transition modes, and you have this drivability problem, which is why a traditional HCCI engine never made it to the market. It was good in the labs, it was good as maybe a concept, but customers couldn't accept it. So this was the challenge that we were up against. We knew that compression ignition was really our solution to getting 30% improvement CO2 or 30% CO2 reduction, right? So we thought long and hard about it, and you know, we finally came to this breakthrough about 2 years ago when we realized, well, we have to have the spark plug inside the car anyway. Why don't we use this as a means to actually control this compression ignition process and when it happens? We call this process, spark controlled compression ignition, or SPCCI for short. How SPCCI works is basically we have to design an engine with a very, very high base compression ratio so that you could compress the air and fuel inside the engine to a very high temperature and pressure, just below to the point where it's about to go bang, okay? Afterwards, we light off a small spark. The spark creates a fireball, and this very small fireball further pushes all the contents inside the combustion chamber into a higher pressure, yet higher temperatures. Once it exceeds what we call the compression ignition threshold, temperature and pressure-wise, everything inside the cylinder, all this lean, all the lean contents inside the cylinder spontaneously combusts. It's like it's a chain reaction. It's so fast. It happens everywhere. Here's a simple animation of it. All the air and fuel inside the cylinder are compressed to a very high compression ratio, 16:1 in our case. We light off a small spark, and this spark creates an expanding fireball that pushes all the other contents inside the cylinder or combustion chamber into compression ignition. And boom, we get compression ignition very quickly. We can also control when this compression ignition event happens by changing the timing of our spark. The next problem is lighting a fireball. As we mentioned already, when you're trying to light a barbecue fire with very little lighter fluid, it gets very difficult. We already mentioned that the contents inside of the combustion chamber is very, very lean. So how are we going to light a fireball when there's so little fuel inside? Just as this graph says, basically, the leaner we get, the harder it gets to get a fireball to light and propagate controllably. The obvious solution is, well, we could put more fuel into it, okay? But when we put more fuel into it, we start losing all the benefits that we talked about in lean combustion. We get more creation of emissions, and we also get more heat wasted. And also, we don't have the low CO2 content. Our solution was this. We'd actually have to create a region near the spark plug that's just slightly less lean. I say slightly less lean because it's not actually rich. It's not lambda less than 1. It's still on the lean side. But by creating a local region near the spark plug, this is a side view of the combustion chamber on the top view. We see this area that's just slightly less lean. That allows us to actually light off a fireball that will propagate throughout the cylinder and cause compression ignition. Now, we can't just put fuel in and make it slightly less lean because it'll just mix with everywhere else. So in order to cordon off this region of slightly less lean and very lean outside of that, we need to introduce, not a laser, but a cylinder swirl. Okay, so it's kind of like a vortex of airflow inside of your cylinder. And this vortex has, like a hurricane eye, a very stable center. And that stable center is where we can inject a little bit more fuel to let our SPCC fireball initiate and start. We create this swirl inside the cylinder through our port design in the cylinder head, and also because we have a lean supercharger that helps deliver a high amount of flow. The more flow, or harder is blowing, the more turbulence and vortex we have. So that's one solution. One other problem is that we have to prevent pre-ignition. We have an engine now that has a very, very high base compression ratio. That makes it very, very easy to knock. Now, as Dave said, in our skyactiv gas engine, we spent all of our efforts trying to prevent knock. Well, this is a slightly different type of knock because it happens even before the spark plug lights. The compression is so high that the temperature and the pressure inside the cylinder can already let just the fuel and the air auto-ignite on its own. We want compression ignition or knock, but only at the right time. If it happens while the piston is still stroking up, you could have catastrophic effects. You could break pistons, bend rods, so we need to absolutely prevent this. In a traditional gas engine, the fuel is injected during the intake stroke. As the piston is stroking down, it's sucking air in as well as fuel. The fuel sits inside the cylinder and it has a lot of time to soak up all the heat from surrounding cylinder walls, and as it gets compressed, it gains heat and pressure. It might gain so much heat and pressure that at one point it exceeds the auto-ignition temperature or pressure threshold, this red line that we have up here, okay? At that point, you have knock while the piston is still stroking up. So in order to prevent that, and just a little explanation, this is the intake stroke as we're stroking down. This is a compression stroke as you compress everything. And then this is the beginning of the power stroke or the expansion stroke right here. We want everything to happen right where we have the spark plug happen. We don't want the pre-ignition event. So our solution was this. Let's break our injection events into multiple phases, okay? Initially, we give a very small squirt of fuel so that it's so lean, regardless of the conditions, it will never pre-ignite. So as it's stroking down, sucking it in, this fuel atomizes, sucks in heat. Then during the compression stroke, we give a larger injection of fuel under higher pressures that atomizes, but doesn't have the same amount of time to heat up. In that way, excuse me, in that way, it doesn't have enough time to reach the auto ignition temperature threshold. We can then control when it lights through our spark plug. So, in a way, compression ignition is like playing with fire. We can reap a lot of benefits from using compression ignition. Thank you so much. Yeah. We can reap a lot of benefits from compression ignition, but if it's not just done right, we could get burned. So we need to monitor the entire compression ignition process. As we described before, it starts with a spark ignition that builds an initial pressure rise. Once this pressure rise raises a threshold temperature and pressure for compression ignition, we get this very rapid, spontaneous event. And the ideal case is to keep this compression ignition event right after top dead center so you get the maximum power out of that stroke. Well, there's a problem. In the lab, this is great. When you're outside, temperature, pressure, humidity, all of these things change. And when these things change, it might take a longer time for you to actually get to this compression ignition threshold. That way, we don't get compression ignition happening when we need it to. We get less power out of each stroke. The obvious solution is that we need to change our ignition timing relative to our ambient conditions. So this is what we do. In SPCCI, inside the engine, we actually place cylinder pressure sensors in each and every cylinder. We're constantly looking at the pressure rise profile in each cylinder, and we're adjusting the spark timing. We have an ideal case where this is the rise rate so that we could keep the peak pressures right after top dead center. And when we see something that's contrary to that, we adjust at the next combustion event, at the next cycle. This way, the cylinder pressure sensors not only let us monitor and control SPCCI, but it also acts as a way to predict knock, predict abnormal combustion, as well as detecting knock in itself. Hopefully it never knocks or it never pre-ignites because we're already seeing trends and we can back off or change the spark timing to compensate for that. Okay, so these solutions, along with a lot of other much more complicated ones, kind of led to this breakthrough that we call SPCCI. It's what makes compression ignition possible in our skyactiv-x engine. Because we're running the spark plug all the time in both compression ignition mode and spark ignition mode, we can actually drastically expand the range of compression ignition throughout most engine RPMs and engine loads. Only at the very high engine speeds do we switch back to a spark ignition mode. And not only that, because we're using the spark continuously, we can kind of phase in and out of the two modes very seamlessly, so we can avoid the problems of what other OEMs had run into. When you guys drive these vehicles, you'll actually notice, like, I don't feel any difference. It drives just like a regular gas car, which is really the amazing part. If you're not noticing anything, that's a good sign. So this is what skyactiv-x and SPCCI looks like. Here you have the intake stroke, air, fuel, and it starts creating this swirl inside the cylinder. And when we get to top dead center, near top dead center, we initiate the SPCC spark. The fireball expands and pushes everything into compression ignition very, very fast. And here's our exhaust stroke. So just notice how fast everything's happening instead of compared to like a spark ignition where it takes time. As the piston's already moving down, it's still burning. Okay, so now that we understand the benefits of compression ignition and all the challenges and how we're controlling compression ignition through SPCCI, we could talk about the actual engine that we're packaging it into. skyactiv-x is very much like a normal engine, 4-cylinder, dual overhead cam, 2-liter displacement, aluminum construction. It's tuned to run on 87 octane gas, but notably, it has a very high compression ratio. We call it 16:1 right now. Depending on markets, fuel conditions, regulations, all these might change, but 16:1 is about the ballpark that we're seeing that's necessary to get just to before the compression ignition threshold. Also, in all the new skyactiv-x engines, we're going to feature mild hybrid electrification. This entire belt and pulley and alternator assembly up front that you'll see. To control the SPCCI process, excuse me, we had to add a couple more additional pieces of hardware onto this engine. They're not pioneering technologies by any sense. They all exist, but these allow us to have all the levers and switches to change everything so that we can control compression ignition at all the time. So we start with, as I mentioned, a higher pressure fuel injection system that promotes atomization, reduces emissions, but also helps with mixing. We have the in-cylinder pressure sensors, which you can't really see here, but they're right at the very top of each combustion chamber. You might be able to see it here on this engine. In addition to that, we have a high response air supply. That's kind of complicated wording for basically a lean supercharger. We're just shoving a lot more air into the engine all the time because we want to burn lean. We need more air. Now this supercharger is a low boost roots type compressor on a clutch, so we can engage it and disengage it when we need to. It only comes into operation at higher engine loads. But the point is that we don't want people to walk away with this wrong impression that this is a supercharger and on a 2-liter engine and have ridiculous power expectations out of this. The purpose of this is to increase specific heat ratio by putting more air into the cylinders. All that's fed through an air-to-water intercooler, so the supercharger feeds down, routes back up, and comes back into the intake. Part of this lean air that we put into the engine is EGR, exhaust gas circulation. But because it's so hot, as Dave explained, we need to cool it down. So we employ a technology that's used on our SkyActiv turbo engines. It's basically a cooler, takes exhaust gas, cools it down, gets it ready to be reintroduced into the intake. Now, this exhaust gas isn't part of the combustion. All it's there to do is to suck up the energy of combustion and help expand it again and push the cylinder down some more. Because everything's happening so much faster, we need to also use electronic valve timing actuators. In the skyactiv G engine, we use a hydraulic actuator on the exhaust side because the response time wasn't as critical on the exhaust side, but now with SPCCI and skyactiv-x, we need a very fast response rate on both intake and exhaust cams. And as I mentioned before, there's a mild hybrid system. That's mostly for energy recovery during deceleration, electrical energy recovery, as well as start-stop operation. You'll notice here there's actually a flange for a conventional starter motor for normal start, and then this big monster alternator and the pulley on top of it is to help restart the engine when you're just doing idle stop operation. Okay, so that's skyactiv-x, the engine itself that you're going to drive in these prototype cars. How is it better? Well, contrary to our intuition, now that we're trying to save the environment, we're burning less gas, skyactiv-x actually lets us have better performance. The reason why it does that is because of, again, compression ignition. We're anticipating on seeing about a 30% gain in torque over our current generation 2-liter skyactiv G engines. The reason why is because compression ignition happens so fast that all the pressure released at the same time pushes the piston down in a harder fashion. That force of the piston moving down literally translates to torque. So, like a diesel engine using compression ignition, we get a lot more torque gains, especially at the low RPM. Low RPM torque, especially on the street, is what increases drivability. Everybody likes a big American V8 because it's very, very drivable. Why? Because it has torque right off the bat. So this is the main benefit, performance benefit of skyactiv-x. Incidentally, I do want to point out, the car is tuned for 87 octane, but it will run a whole gamut of fuels, all the way up to 92, 93 octane, just because of the SPCCI process. And similar to our Skyactiv turbo engines, the torque peak will move with the change in octane of gas, and that just results in slightly different performance feel. But there's no diminishing, there's no reduction of torque. There we go. Of course, we expect to have great fuel economy as well. In this graph, we see fuel economy for you engine geeks. This is BSFC, and then engine load. When you compare our old generation shared platform MZR engines to our current skyactiv-G engines to the new 2-liter skyactiv-x engines, you'll see on average about a 20% gain in fuel economy. That's again, of course, through the benefits of compression, lean compression ignition. More importantly, if you look at the profile of this graph, it's really broad and flat over this wide range of engine loads. It doesn't have just one little sweet spot. That actually affects how real-world fuel economy gets better, and that's really important to us as a brand at Mazda. Now, of course, this just shows 2,000 RPM. If you want to get a bigger picture of how the car does over a wide range of operating conditions, we would have to put slices of different engine speeds on top of that and build out a 3D map. So another way to look at that is, let's assign a color to each range of fuel efficiency. Black up here being really thirsty, orange, not so orange, is actually very efficient. And we stack up all the different slices for all the different engine speeds on top of that. And then we come up with this 3D-ish map, rotated on its side. Here, imagine this orange area as being the topmost layer of a very efficient, think of it as a cake. Each color represents a layer, stack them on top of each other, and you have a fuel economy cake, for lack of a better term. You have cakes of different shapes. A skyactiv-G cake is a little shorter, a little peakier. A skyactiv-x cake is taller and broader. Now, the reason why this matters is that most engine designers right now target this concept of downsized turbocharging, right? We use less displacement, which means less fuel while you're just humming along. But the instant that you need torque or to accelerate, you have this very thirsty turbocharger that kicks in and then it uses a lot of fuel. An engine like that, it actually has a very peaky fuel economy cake. While it's running on just its 3 cylinders or its lowest displacement, it's on its high peak. But the instant the turbo kicks in, you fall off the cliffs on the side. That's why most of these engines have to be coupled with a CVT transmission, because it needs to be kept in the sweet spot, right, on this peak. But as we know, driving these things usually doesn't result in a lot of driving pleasure for us. So skyactiv-x allows us to not only make a taller cake, but a broader cake. The same yellow region now expands all the way out here. Well, the reason why I have to explain this strange concept of a fuel economy cake, because I can't call it an efficiency island, which is more complicated to understand, is it leads to the next point. And this is what you guys will really feel when you get into the cars and drive it right off the bat. Okay. Most transmissions are designed with fuel economy in mind. We have to save gas by staying at a low RPM at highway speeds, right? Some manufacturers just add a lot more gears onto it, so that at 8th gear or 9th gear on the highway, you're just sipping gas. But the instant that you need to accelerate, nothing happens, because you need a downshift, because there's no torque available in that gear. Skyactiv-G actually also suffers from this problem, not nearly as much, but we had to set the final drive ratio so that it stayed on a higher level of the fuel economy cake than, let's say, at 3,000 RPM. So our final drive ratio was set so that, let's say, at 60 mile per hour, we're running at 2,000 RPM instead of 3,000 RPM, which uses a lot more gas. Now, you might already figure this out. On a Skyactiv cake, we're running at the same layer, 2,000 RPM or 3,000 RPM. Suddenly, we don't have this compromise or this constraint to run low RPM. And as you guys all know, RPM typically means more power, better response. So now we can gear our skyactiv-x car with a shorter final drive ratio so that we can run at 3,000 RPM on the highway all day long with no fuel penalties. That means you have better drivability, you have the same great fuel economy. There's no trade-off. What's that? Noise? Yeah, actually, if you guys look at the cars, there's another entire realm of NVH packaging that we took these cars to in order to control the noise of both compression, ignition, combustion, and the higher RPM and all that. If you guys have noticed driving some of our 6th generation cars, as they've progressed, they've gotten a lot quieter. We've taken NVH very seriously, and we've also applied that in leaps and bounds above and beyond in the 7th generation cars. And Dave will talk about that a lot more too. So that's actually a great segue. Now we have a fun driving car. You don't have to mash on the gas all the time, so you actually become very smooth and controlled with your inputs. It's very direct, fun. Now Dave will talk about the next generation chassis concepts, which are also in the cars, these prototype cars that you guys are going to be driving. I'm sorry, cut you short, right. I forgot about this slide. Yeah, so nutshell, okay. SkyX is a revolutionary way of burning gasoline. It's the first commercially applied use of compression ignition for gasoline in the world. It's completely controlled through a process we call SPCCI. And it's how we plan, it's one of the major tools that we plan to use to help us reduce our environmental CO2 footprint. For me as an engineer, the most important part of it is that skyactiv-x is just this continuation of our Hiroshima spirit, our can-do spirit of being the underdogs. You know, we brought you things like the rotary, the Comprex, skyactiv-g, now skyactiv-x. Basically, Hiroshima's spirit is us giving you things that everybody else tells you is impossible to do. So that's what we're more proud of as engineers. And so with that,